Hi guys, Miss Brumwell here. This is the last video for chapter 1. So a little bit more from 1.5, just a couple examples. I briefly mentioned in the first video that anytime I have a limit when x approaches infinity or negative infinity, that actually results in a horizontal asymptote. So whatever our limit is as x approaches infinity or negative infinity is where the asymptote is. So it's going to be at y equals that value since it's horizontal. Okay, so we're going to find the horizontal asymptotes if there are any of this function. So remember, one of the things we looked at is when I find the limit as x approaches, let's start with positive infinity, okay, of this function, we have 3x minus 2 over 4x plus 1. Remember, I can just look at the leading power, so the highest term in the numerator versus the highest term in the denominator. So when I do that, and I have x to the first and x to the first. So this coefficient, 3 and 4, can come out front and multiply by the limit as x approaches infinity of x over x. Well, we know that that's going to be 1, so we get 3/4 times 1. So my limit is 3/4. So what that means is we have a horizontal asymptote at y equals 3/4. Okay, now we do need to check both sides. We need to check when I approach positive infinity and negative infinity. So we're going to do the same thing, and we can actually kind of jump right to this step, okay? Right? We get, I'll write this part, of f of x equals, so we got 3/4 times the limit as x approaches negative infinity of x over x. So it's just a good idea to make sure you check your signs. So negative divided by negative, though, would still be positive 1, so we end up with the same thing. So because it's the same thing, that means I only have one horizontal asymptote. So it's possible to have 1, 2, or none. Okay, we can't have more than 2, and I guess that's really the basis. 1, 0, or 2 can't have more than 2. This picture is an example of when we have 2. Okay, so let's look at another example. Okay, we are going to find any asymptotes here. Okay, so when we approach negative infinity, okay, I'm going to compare those top values. Okay, so remember, and this is actually asking me to find vertical asymptotes as well, so we'll come back to that one in a second. Let's do horizontal. It's based on what we just did here. So we're going to find the limit as x approaches both negative infinity and positive infinity. Okay, so negative infinity, same thing. I can look at the highest powers. So I'm going to get 3/2 times the limit as x approaches negative infinity of x squared over x squared. That's going to equal 1, right? Negative squared is positive, divided by negative squared is also positive. So we end up with 3/2. I'm going to get the same exact thing when I do positive infinity. So the limit as x approaches positive infinity is also going to be the same thing, but positive divided by positive is still 1, so we get the same thing. So what this tells us is we have a horizontal asymptote at y equals 3/2. Okay, so because we looked at those limits approaching infinity, we know we have that horizontal asymptote. Now vertical asymptotes. Okay, this is where I'm looking for, do I have anything approaching infinity? And remember, we need to decide what should x approach when we're looking for a limit. So how I find that is I need to determine what's not in our domain and look at what happens as we approach those values. So let's find our domain here. So a little easier way to look at this is maybe factored. So this numerator can factor here and turn into difference of squares minus 2. Okay, so there's my numerator completely factored. My denominator, okay, a is not 1, so I want to look for 2 times 10 is 20. Okay, so remember, I want to look for numbers that multiply to be 20, that would add to be negative 9. Sorry, I said that backwards. No, maybe I didn't. Multiply to be positive 20, add to be negative 9, those numbers should be negative 4 and 5. So if I rewrite this guy as 2x squared minus 9x, sorry, I just did that backwards. Okay, so I'm breaking negative 9 into negative 4x and negative 5x. And then I'm going to factor by grouping. So I can factor a 2x out of here. and I can factor a -2 out of here. We always want to take whatever that leading coefficient sign is. Oh, sorry, not -2, -5, excuse me. -5, and then we're left with x minus 2. Remember, the goal is to get those to match, so this will turn into those two terms become one of my factors, so 2x minus 5, and the matching term becomes my other factor. Okay, so here's my fraction. All right, so what can x not be? Well, it can't be whatever makes my denominator equal 0, right? So if I can see this one right away. X cannot equal 2. Okay, what can x not be here? If it's hard to just look at and tell, remember you can set this equal to 0 to find it. So we don't want it to equal 0, so whatever value this is, it's what x cannot be. So if I add 5 and divide by 2, we get 5/2. So those are the two things that x cannot be, right? They're undefined for this function. So those are the values we want to look at for limits, okay? All right, remember we actually only have to look at one-sided limits. So if one side approaches infinity, it's automatically a vertical asymptote. So let's take a look. So let's start with 5/2, okay? So I'm going to look at the limit as x approaches 5/2, and let's do from the left. So we're just going to do one side, okay? You only have to look at one side, not both. Of f of x, or r of x, I guess I better use that same notation, of r of x, okay? All right, so what do we got here? Well, I could have simplified this, right, by dividing out those x minus 2's. So I'm going to do that. So we got the limit as x approaches, sorry, I'm going to actually do this down below so I get a little room left over here. So I'm going to just keep going lower. Okay, so equals limit as x approaches 5/2 from the left of, okay, so if I had canceled those x minus 2's, we'd have 3x plus 2 over 2x minus 5. Okay, and so if I were to substitute, okay, 5/2 in here, I'm going to get a constant, right? This is 2.5, right? So 3 times 2.5 plus 2, that's going to be some constant number. So this is going to equal a constant, okay, over, okay, so if this is 5/2, this would equal 0. So it doesn't equal 5/2, it's something just a little bit less than 5/2, getting closer and closer to 0. So if it's less than 5/2, this is going to be a very small negative number, right? Okay, so if this is a very small negative number, remember a constant divided by a very small negative number means it's approaching negative infinity. And if a limit approaches infinity or negative infinity, that's a vertical asymptote at this value. So this one indicates we have a vertical asymptote at x equals 5/2. Okay? All right, now we have to check the other value, 2. All right, so we're going to look at the limit as x approaches 2. Now this one, I'm just going to show you guys what happens. We can also look at a one-sided limit here, but I'm just going to look at what happens. So this was the problem, right, for 2. Well, we could cancel that out. So then 2's no longer going to be a problem. So if I were to find just the overall limit as x approaches 2, if I divide those out, we have the limit as x approaches 2 of 3 times x plus 2 over 2x minus 5. So because we divided out the part that was going to make 2 an issue, I'm okay just substituting in 2, right? So we have 3 times 4, 12, 2 times 2, 4 minus 5 is -1, so we get -12. So what that means, if I didn't get infinity or negative infinity, that means x equals 2 is not a vertical asymptote, okay? So we only have these two asymptotes. So this means no vertical asymptote at x equals 2. Instead, this is a hole. That's when that'll happen. This is a hole, okay? So if we don't get an infinite limit, okay, and we actually get a value, it's a hole instead of a vertical asymptote. All right, last example here, 1.5. An application here of some of our limit stuff. Okay, so we have salt dissolves in water into sodium ions and to chloride ions according to the law of inhibited decay given by this function. This should hopefully look familiar to you from pre-calc and algebra 2, where A of t is the amount in kilograms of undissolved salt present at the time t in hours. A sub 0, or A naught, is the original amount of undissolved salt. K is some negative number that represents the rate of dissolution. Okay, so if initially we have 25 grams of undissolved salt, and after 10 hours there are 15 kilograms of undissolved salt remaining, how much undissolved salt is left after 1 day? So this is an exponential decay problem, right? This is an exponential function. Okay, so we need to find our rate of decay. They don't give it to me anywhere. They don't tell me that rate of decay. They just tell me that K is the rate, and it's some negative number because that amount of undissolved salt gets less and less and less over time. Okay, so let's see what we have. So initially, that's kind of keyword. Initially, there's 25, so that's my A naught. Okay, and then we're given some time, 10 hours, and then we're given a new amount. So this is A of t. In particular, it's A of this t. So I'm going to plug in 15 for A of t. So I'm looking at this equation right here. Equals 25 E, we don't know K, and we know T right now is 10. So this time and this amount of undissolved salt go together. We're going to solve for K to be able to answer this question about how much undissolved salt would be left after 1 day. Okay, so to solve this, I'm going to first divide by 25. Okay, so I'm going to simplify that to 3/5 equals E to the 10K. Okay, we're solving for K. Remember, the inverse of E is natural log, so I'm going to natural log both sides. The natural log of E is just 1. And then this guy comes down. So we have natural log of 3/5 equals 10K. To get K by itself, we divide by 10. So I've got natural log of 3/5 divided by 10. So I put that in my calculator and I got approximately negative 0.051. And they did tell us it was a negative rate of dissolution, so that fits. Now they're asking, now that we know the rate of decay, how much undissolved salt is left after 1 day. So remember, this T was an hour. So we have to think 1 day, T is 24. So now I'm asking, okay, what's my new amount? So I don't know this. We're still starting with that initial amount of 25. E to the K, we now know K is this, negative 0.051. And then the time we care about for that question is 1 day or 24 hours. Okay, just plug and chug that into your calculator, enter that all in. We get, and actually my time here is 24, so I could actually put it like this. So A of 24, so after 24 hours, the amount of undissolved salt left is about 7.337 kilograms. Okay, so to answer how much salt is left after 1 day, that is how much. Okay, all right, how long will it take a ½ kilogram of undissolved salt to remain? So I'm asking, when is my new amount going to equal a half? So everything else is the same, but this time we're looking for T. How long? So we have negative 0.051 T. So this one looks actually very similar to how we started part A. I need to get something in the exponent by itself, so we're going to first get rid of this coefficient. So if I do this, divide by 25, I'm going to get 1 over 50 equals E to the negative 0.051 T. Now natural log both sides to get rid of our E. So we have natural log of 1 over 50 equals negative 0.051 times T. Divide by that. So we have T equals natural log of 1/50th divided by negative 0.051. Okay, so that's my time. Plug that in our calculator to get an approximation. And we get approximately 582. All right, so this is the amount of hours it will take. So after, or I guess we'll just add this label. Okay, hours. All right, now part C says find the limit as t approaches infinity and interpret its meaning. Okay, so we're finding the limit as t approaches infinity of kind of our generic function. So we're going to plug in k. So we have our initial amount, 25 e to the negative 0.051t. So that's kind of my function, right? So as time approaches infinity, remember negative exponents I can also write like this. I can move it to my denominator and make it positive. So we can also write this as 25 over e to the positive 0.051t. So remember, this is a constant, and this is going to approach infinity. Anything raised to a power is just going to get bigger and bigger and bigger and bigger. So a constant over a very large number is going to approach 0. Okay, so what does this mean with the context of this problem? Okay, so t is time, remember. So if time goes on forever, time approaches infinity, this function should approach 0, which makes sense, right? As more and more time goes on, less and less undissolved salt should remain, and it should approach 0. So as t approaches infinity, the amount of undissolved salt remaining approaches 0. All right, okay, that's it for this video, guys. Thanks for watching.